Hey everyone, Mr. Schachter here with some exciting related rate practice problems. This video we're going to use related rates to differentiate equations involving two or more variables. Let's get started. Example number 1, life of pi. A boat is being pulled towards a dock by a rope from the bow using a tool that is 6 feet above the bow. If the rope is pulled in at 2 feet per second, how fast is the boat approaching the dock when 10 feet of rope are out? All right, there's a lot of information here. Let's see if we can draw a picture to better understand the problem. So I'm going to go ahead and draw a picture. I'm going to draw a picture of a boat, which we're just going to just do a little bit of this, I guess. Here we go. Nice boat. That's the best boat ever, I know. This is my boat. And then what's happening is I have a dock. That's over here. This is my dock. Okay. Here you got a little bit of water. And then I have a rope, and this rope is basically pulling my boat in. Here's my rope, And this is the other measurement in this problem, the distance away from the boat and the dock, which we can call whatever. I'll call it x, okay? And we'll call rope R, R for rope. Now let's see what I know. In this problem, we know what is the rate that we're given. Now you can always find rates in the directions because they're given in rates of change. So the rate I'm given is 2 feet per second. It says if the rope is being pulled in at 2 feet per second, that means in this problem that dr dt equals 2 feet per second. Okay? dr dt because it's the rate of change of r, the rate of change of the rope with respect to time. And let's go ahead and examine what is the rate that we need. Well, the problem goes on to say, how fast is the boat approaching the dock? The distance between the boat and the dock is x. So if I want the rate, how fast, I need dx dt. Those are the two rates that I need. And the last piece of information that I'm going to be able to use is the fact that the tool is 6 feet above the bow. No matter what happens in this problem, this distance will always be 6. Okay? It will never change. It will never be a different value. However, this piece of information, which I'll use pink for, 10 feet of rope are going to be out at the end of the problem. That is not something I could plug in my problem right now. If I plugged 10 in for R, and I took the derivative of 10, it would go away. R would be gone because the derivative of 10 is 0. This piece of information I call frozen information, meaning that if I plugged it in the problem right now, it would freeze frame my problem, and then the rope could no longer change. I can't plug 10 in until after I differentiate. You can't plug frozen information in until after you differentiate. Okay? But we're getting a little ahead of ourselves. I just wanted to make that clear. What is the formula that will relate these things? I'll give you a hint. This is a right triangle. It is Pythagoras. So a squared plus b squared equals c squared. You have two sides of a right triangle that are changing. Let's go ahead and fill in our information. This is going to be x squared plus 6 squared is equal to the hypotenuse r squared. And lastly, before I take the derivative, I'm just going to call that 36. Okay? Now, the goal is to differentiate this equation with respect to time. So all you need to do is use your normal derivative rules, but slap on a d blank dt to every variable. Let's give it a try. The derivative of x squared using normal derivative rules is 2x, but since I'm differentiating with respect to time, I need to add a dx dt. That stands for the derivative of x with respect to time. The derivative of 36 is 0. The derivative of r squared with respect to time would be normal derivative rules, 2r dr dt. Now, this is the formula that I need to plug stuff in and solve. Okay? Well, interestingly enough, here's where I can use my rate. Okay? dr dt is 2. So I'm going to go ahead and plug that in. So 2 r, we'll just leave r blank for a minute, and dr dt is 2. And then over here I have 2 and then some value of x, and dx dt is the only variable I'd like to leave in the problem. Everything else I should be able to find. Now, here's where I'm going to use my frozen piece of information. This 10 right here, okay? This 10 can now be used. I want to look at a new triangle where this is still 6, it's always 6, but R now, there are exactly 10 feet of rope out. The question is, how big is X? Well, I could solve for this, right? If I solve for this, it's a 6, 8, 10 right triangle. So X equals 8. Or you could just use Pythagoras, 6 squared plus blank squared equals 10 squared, and solve for 8. Or this is a Pythagorean triple, so I already knew it without doing the math. So X is 8, and of course we just used R as 10 in the problem. R is 10 in the problem. And so really if I needed to get dx dt, all I have to do is 2 times 10 times 2 divided by 2 times 8, and I get the answer of 2.5 feet per second. My answer, of course, is a rate of change, so its units are feet per second. Example number 2, Deepwater Horizon. Oil spilled from a tanker spreads in a circle whose circumference increases at a rate of 40 feet per second. How fast is the area of the spill increasing when the circumference of the circle is 100 pi feet? All right, I'm not going to draw a picture here. We all know what a circle looks like. It honestly wouldn't help us too much. So let's go ahead and identify the rate that we know. The rate that we know in this problem is right here. It's 40 feet per second. And that's the rate of change of the circumference. So we know dc dt is equal to 40 feet per second. Okay? And the second rate that we need, the rate that we need to find, it says how fast is the area of the spill increasing. So we need dA dt. When asking yourself what formula relates the area and the circumference, unfortunately there isn't one, right? There isn't a simple formula for area of a circle that also includes circumference. But we can be a little creative here. We know that the circumference of the circle formula involves the radius, right? And the area of a circle formula also involves the radius. So I think I can get away with it. Now, the formula that I need to stick to is the formula that I need to solve for. So area of a circle is my go-to. So area equals pi r squared. This is certainly the formula that I need to take the derivative of in order to get a dA dt, which is what I need to solve for. Okay? The right side of the formula is pretty easy to differentiate, keeping in mind that pi is a constant. So if I use my normal derivative rules on r squared, the derivative is simply 2r to the first power dr dt. Now, I actually only need to solve for two things. I need to solve for r and dr dt. And once I have those, I can find dA dt. But unfortunately, I don't have those right now. But I can get a little creative. Here's what I can do. I know the rate of dc dt, the rate of change of the circumference of the circle. So let's go ahead and build the circumference of my circle. 2 pi r. Let's go ahead and take the derivative of the circumference of my circle. The derivative of circumference is dc dt. The derivative of 2 pi r using your normal derivative rules, the 2 pi is just a constant. So 2 pi, and the derivative of r is just 1, it goes away, but I need a dr dt. And so I can actually use my dc dt here is 40 to find dr dt. So dr dt is simply equal to 40 divided by 2 pi. 40 divided by 2 pi. And this is actually going to equal, you know what, let's just leave it for now. We'll call it 20 over pi. The rate of change here would be feet per second. So I have one of the things that I needed. I have dr dt is 20 over pi. But I don't yet have the value of r. That's when I need to use my frozen information here. It says that the circumference of the circle is 100 pi. All right? So let's see if I could do just one more equation to find out what r would be. If the circumference is equal to 2 pi r, and the circumference was provided as 100 pi, I can simply divide both sides by 2 pi and get r as 50. And that is the last piece of information that I need in order to solve the equation. So I'm going to go ahead and plug everything in its place. So dA dt is equal to 2 pi times 50 times 20 over pi. And this is going to give me an answer of 2,000. Now it's a rate of change of area, so it's going to be square feet per second. Square feet per second. And if you need to prove it to yourself, you can look at the 50, which would have been measured in feet, and you're multiplying that by the rate of change of feet per second to give you feet squared per second. And that would be the rate of change of the area with respect to time. Example 3, The Wizard of Oz. The figure below represents an observer at point A, watching a balloon B as it rises from point C. The balloon is rising at a constant rate of 3 meters per second, and the observer is 100 meters from point C. Okay, so let's chat. Letter A asks to find the rate of change in x at the instant that y is equal to 50. So let's go ahead and identify. We know, in this problem, we know it says 3 meters per second is the rate of change of the balloon rising, so that's going to be dy dt is equal to 3 meters per second. That's this distance right here. And then it says the observer is 100 meters from point C. Okay, and that's fine. That's 100. That's constant. No matter what happens in this problem, that will never change. So I can automatically assume that from the get-go. A says to find the rate of change in x. That's pretty easy. We need dx dt. Now it also says at the instant that y is equal to 50. Unfortunately for us, y is changing over time, right? So this is frozen, and we don't put frozen information in until after we differentiate. So the question is, what formula relates these rates? And that would be Pythagoras. It would be x squared equals y squared plus 100 squared. Or if I clean this up a little bit, actually, you know what? I don't even need to, because the derivative of the 100 squared is just going to be 0 anyways. Why don't we just differentiate? The derivative of x squared with respect to t would be 2x dx dt. Derivative of y squared would be 2y. Oops, I was about to do a dt over there, not like that. 2y dy dt, and the derivative of the 100 squared is just 0. And so I ask myself, what do I need here? Well, dx dt is the variable that I need. That means that I should be able to find x, I should be able to find y, and dy dt, but I already know dy dt. So let's find x, let's leave dx dt, let's find y, and then dy dt is given to me as 3. So let's think for a minute here. If I've got this picture in this Pythagorean theorem, and I plug in a 50 for y, I can do x squared is equal to 50 squared plus 100 squared. And so then after a little calculator work, we get x is approximately 111.803. That's x. I'm going to put that into x, 111.8, and I'll just leave it like that. And then the y I just plugged in was 50. So after a little bit of calculator work, dx dt is going to equal 1.342 meters per second. This is the rate of change of x over time. Okay? Let's try b. Let's go ahead and get rid of this work, just so we can have a little bit more room. Let's see. b this time. We'll put b right here. Find the rate of change in the area of the right triangle BCA at the instant that y is 50. Okay? Y is 50 again is frozen. The rate of change that we know is still dy dt. The rate of change that we need is the area of the right triangle. In that case, we just need the derivative of the area of the triangle with respect to time. So what formula is going to relate the area and the one side of the triangle? It's just the area of the triangle. And the area of any triangle is 1/2 base times height. With the area formula, though, remember that the b is constant in this problem. It's 100. So actually, this area formula is equal to 1/2 times 100 times h, which is just equal to 50h. So then if I go on to differentiate, the derivative of area with respect to time is equal to, now the derivative of 50h is just 50 dh dt. So in this case, dh dt, which is just the height of the triangle, which I actually just could have called the y, so I'm just going to go ahead and call that a y. Yeah, sure, we'll call it a y. And dy dt is equal to 3. So the answer is 50 times 3, or 150. Now this is a rate of change of area, so it would be meters squared per second. Right? Rate of change of the area of this is 150 meters squared per second. Last problem, letter C. Let's get a clean page for letter C. So C. Find the rate of change in theta at the instant y is equal to 50. So in this problem, we still know the same rate of change, that y dt is equal to 3 meters per second. And we need, the problem is asking for the rate of change of theta, so which is just d theta dt. So the question is, what formula is going to connect theta and the value of y? Well, whenever it's an angle, it has to be a trig function. So if it has to be a trig function, I need to use my opposite side, and I need to use my adjacent side, so I'm going to use the tangent. So the formula is the tangent of theta is equal to the opposite over the adjacent. This is my formula I need to differentiate. Well, if I need to differentiate this, why don't we just multiply by 100 and get y equals 100 times tan of theta. All right? This is the formula I need to take the derivative of. So if I take the derivative of y, I get dy dt. And if I take the derivative of 100 tan theta, I'm just going to get 100, which stays the same. Derivative of tangent is secant squared theta d theta dt. D theta dt is what I needed. Dy dt I know is 3, but I don't know theta. But here's how I can find it. So that's that. I know that the frozen information says that y is equal to 50. So if I draw a new triangle, oh geez, you know what, I'm not sure what that was. Let's try that again. If I draw a new triangle, right triangle, theta, y is 50, this guy is 100, I can actually find theta. Tan of theta is equal to opposite over adjacent. And using the calculator's trig functions, I know that theta is going to be 0.464 radians. 0.464 radians. Okay? That goes in here. Then I solve. So I get 3 equals 100 times secant squared of 0.464 d theta dt. So d theta dt is just going to equal 3 divided by all these guys, which, if my calculator serves me correctly, will give me an answer of 0.024 radians per second. And that is the rate of change of the angle theta when y is 20.